So to kind of kick it off, acid soils, those soils that have a pH less than 6 are becoming more common. And from the laboratory side, we've been getting a lot more questions about liming in regions that have never limed before. So some of the areas where that is really kicked off is Southwest North Dakota, North Central South Dakota, and also Central Montana. And the big driver behind this has been the advancements in precision soil sampling, both zone and grid, depending where you're at. And it is starting to find these very low pH pockets inside of fields. Normally, when we were just taking whole field composites, it would completely mask over the high pH and low pH areas in the field. But now with precision soil sampling, we're starting to parse those out. Other things that have prompted questions. We analyze buffer pH, which is what is used to figure out lime requirement at no cost on our composite soil samples if they have a topsoil pH less than 6. And so some producers have been seeing lime requirements on their soil test reports that are wondering, well, what is this? So that has prompted further discussions, and we also analyze subsoil pH in all our soil samples. And so in addition to the topsoil pHs being acidic, we also see some more subsoils, this 6 to 24 inch depth that are also acidic. So that, all these kind of questions are pushing in this one direction of soil acidity. So typically, as Ryan had kind of alluded to in the intro, we talk about salinity, we talk about high pH soils a lot in the Northern Great Plains because, for the most part, it is kind of like the dominant theme. But when we start looking at the specific, regions on the map where we see high pHs, it's actually mostly in like, oh, let me grab my pointer. There we go. It's mostly in, the Red River Valley, the Till Plain, and especially up into Manitoba. But if we look into the West River country that is west of the Missouri River, some of that area that hasn't been recently glaciated, the number of soil samples that have a pH greater than 7.3, thinking about our high pH soils, actually isn't that many. In the Dickinson area, only 40% of soil samples have high pHs. And even in the Bismarck area, only 27%, a third. And when we look at the number of soils that have pHs less than 6, in other words, where we start having conversations about acidity and liming, it's a surprisingly number of 13 to 14% of soil samples. And if we go just across the border into South Dakota, into the Mobridge zip code area, 25% of soil samples are actually below 6. So this acidity problem is a little bit more widespread than one would think off the bat. So why are acid soils problematic? And there's primarily two reasons. One is reduced nutrient availability. We classically think about high pH soils tying up phosphorus, but when we go to the low pH side, getting to pHs less than 6.5, especially less than 6 and getting down into the 5s, phosphorus availability goes down, as well as the availability of many nutrients. But the big topic is aluminum toxicity, which happens when you hit a pH somewhere around 5.2 to 5.5, and the amount of soluble aluminum in soil starts going up. And when you have lots of aluminum that is, there in the plant root zone, it starts causing the plant roots to get short, stubby, stunted. And in this photograph, the plants on the right are suffering from aluminum toxicity, and that's exactly what you see. Short, stubby roots, little biomass, and a root system like this doesn't do a very good job of taking up nutrients or water. So that's really why we're concerned about these severely acid soils. And it's a trend that has, continued to grow over time. So I pulled some of the AGVISE soil test data from some of these areas where we have, a lot of acid soils. So thinking of North Central South Dakota, Aberdeen, Pierre, Mobridge, as well as Southwest North Dakota and the Bismarck and Dickinson zip code areas. And if we look back as far as 1998, Dickinson, the line here in blue, it was actually about 8% of soil samples way back then were already below a pH of 6. But as you can see, over the past 22 years here in 2020, we've now hit the point where over 15% of soil samples fall below 6. So this includes, a big trend of soil samples that, it's either that we're finding more or we're doing more soil sampling, one, but the other part is we are starting to just overall see the net effects of acidification, and especially in a no-till setting. And in a no-till setting, we tend to get more pH stratification, which kind of further complicates this issue. In conventional tillage, if we were incorporating, the top 4 to 6 inches every year with a chisel plow or a field cultivator, we end up mixing that acidity, and it is quite distributed across that 0 to 6 inch depth. The other thing is, if you have erosion, you also start to pick up some high pH subsoil from down low, which helps kind of moderate some of the effects of acidification up top. But in no-till, we no longer have this homogenization, the mixing of this whole topsoil sample, and we start to get stratification up in the top couple inches, usually the top 2 to 3 inches. And so the acidity gets concentrated up top, and this is where we get very low pHs right in the seed zone that causes aluminum toxicity issues. To help us illustrate that point, here's a little case study that an agronomist down by Reeder had found in safflower. In this particular field on the right, you can see there's these kind of open bare patches in among the kind of sporadic safflower stand to start with. On the left is a compared example between the good areas and the bad areas of this field. The good areas of the field had about, plants that were, 2 to 3 inches tall. If you look really close, these little ones here that are no more than an inch tall are the bad areas. He went out and took some soil samples to figure out, exactly what was going on here. And between the good and the bad areas, the topsoil had pHs of 4.5 and 4.3. This is screaming low pH. And when he broke that soil sample up farther into the 2 to 6 inch depth, also found that 2 to 6 inch depth was very acidic as well. So that entire root system was very, very low. And when we look at how much aluminum was created because of the low pH, in the top 2 inches, it was way up at 91 and 25 parts per million, which is a lot of aluminum. If you have pHs that are greater than 6 or close to 6, you shouldn't have any soluble aluminum there that wouldn't create any aluminum toxicity issue. But this is an example of where that's causing a problem. So when you're trying to tackle one of these problematic fields, how do we start? Well, there's 2 things that you need. And one is a pH test. And this is the water 1-to-1 method. And this measures the active acidity, the hydrogen ions that are found in the soil solution. So the pH test tells us what the plant root experiences. And it also tells us if we need to apply lime. It doesn't tell us how much, but it tells us if that pH is low enough where we need to start considering lime in the discussion. Then, if the pH is less than 6, where we start having these discussions, then we run the buffer pH test. And what a buffer pH test does, we use the Sikora method. It measures the active and reserve acidity on the cation exchange capacity. So what this tells us is how much lime is needed to reach our target pH. And for most crops, we would end up liming to increase that soil pH back up to a pH of 6, which is good for most crops. For some more sensitive crops like alfalfa and clover, we would lime it even further to try to get it up to 6.5. Some other helpful information that can be analyzed on these soil samples is the cation exchange capacity, the CEC, as well as organic matter and aluminum. But the main 2, if you're going to need to keep your costs down, is pH and buffer pH. The other information helps us kind of sort out some of the details and figuring, if we really need to apply lime today, is like if we have a lot of aluminum that shows up on the test. The other thing that is needed is precision soil sampling. And like I said before, when we had whole field composites, we masked the low and high pH areas all together. But this is a breakdown of some soil test data from this past year where we took all the soil samples from, these areas with lots of acid soils, the Aberdeen, Mobridge, Bismarck, and Dickinson areas. And within fields, measured the difference from the high testing zone to the low testing zone and figured out what that range was and averaged it across it all. So this kind of gives you a big, broad picture for the role of precision soil sampling compared to just using whole field composites. So the Aberdeen zip code area actually has some pretty good examples of intensive zone sampling. And if you had a 3-zone field, the range from the low side to the high side would be 0.8 pH units. So that could be everything from a pH of 5 to 5.8. If you increase the number of zones within your field, say up to 5, then we increase the range up to 1 or to 1.3. So that could be everything from 5 to 6.3. And if you further increased the number of zones in the field, in other words, we're capturing more and more variability, that pH range within the field goes up to 1.7. So this is just on average. There's of course examples where that pH variability is much worse, and also examples where it's not as bad. If we go to the Dickinson area, there's not a lot of zone sampling beyond 3 or 4 zones. But the key part here is even when we have a zone field with 4 zones in a field, so if it's a 160 acre quarter, these are still 40 acre zones within that field, we're still at 1.2 pH units, which is quite a range within a field. And I bet if we had more precision soil sampling and more detailed precision soil sampling in this area, we would see that pH range increase even further. I know my fellow panelists, I know Brian Arnell is going to talk a lot about precision soil sampling and the need for it to make a variable rate lime application. So I'm not going to beat this horse to death, but this gives you some context for what we're working with in the local area. So lastly, how do we soil sample? Well, first of all, we have to identify the problem. And sometimes we do that with a regular soil test. Sometimes we see whole field composites that have pHs that are below 6 in the 5s. That's a red flag. Other times we have some in-field troubleshooting, like that safflower example where the agronomist or grower might take some plant and soil samples to figure out why we have good and bad areas doing differently. Or you look at your yield maps and we see you got areas that just don't do well year after year. That's probably a good reason to go out and do some more investigation. The next step is moving into zone sampling. And for this, I recommend using 0 to 6 and 6 to 24 inch depths. And we want to keep our regular zone soil samples for developing the crop nutrition plans for nitrogen, phosphorus, potassium, sulfur, etc. Because we're still going to apply our nutrients, in large zones, and because we're going to be soil sampling every year for nitrogen in particular. So we still want to keep our regular zones, but then we need to ask ourselves a couple more questions. Do we have zones with topsoil pHs that are less than 6? And do we have zones with subsoil pHs that are less than 7? In other words, we have acidic subsoils as well. So in these zones, this is where it gets a little bit more interesting because, a 3-zone field with a 60 acre zone is still really, really big. And it's frankly too big to make a lime recommendation work because the cost is just so high per acre. So what we need to do is redefine these specific zones with pHs less than 6. And some good tools there are satellite imagery, because these areas with bad aluminum toxicity are going to take the yield and biomass down to nothing. So there you can start pinpointing these areas in the field. You might even use like a Veris EC card or EM38 to help refine the zones further. What about grid soil sampling at 1 or 2.5 acre grids? Thinking about the cost of lime, this is actually a valid thing to explore because the cost is so high. Grid soil sampling actually is going to pay in this case. Then once we have redefined our zones, we got to resample them to figure out exactly how low that pH is within it. And I recommend using a hand probe because we're going to be splitting depths. Because we have the stratification problem, we are going to be testing, the 0 to 3 inch and then the 3 to 6 inch depth. If all that acidity is up in the top 3 inches, a surface lime application probably can work. But if you have acidity down to the 3 to 6 inch depth, well, we might need to be talking about lime and incorporation. So that gets to be a little bit more interesting as well. If you have a history of deep banded anhydrous ammonia, down to 6 inches or 8 inches or deeper, Then also a 6 to 12 inch soil sample might be important to collect, because your acidity isn't at the surface like most of the broadcast urea cases. In that case, your acidity is happening even lower. On those soil samples, you have to make sure you get a pH and a buffer pH. So those are the two essential parts. And then, of course, the other helpful information is CEC, organic matter, and aluminum. And with that, you kind of have the tools that you need to make a variable rate lime script, which some of my other panelists are going to talk about at much greater length. So what we've talked about today, this is kind of our visual checklist so far. We got to identify the problem. We've done that. Also talked about measuring the severity and the extent of the problem, which requires soil testing and specifically precision soil sampling. The next things that we'll be talking about are choosing a mitigation strategy, which might be liming. It might be seed place phosphorus. It might also mean acid tolerant crop species. And depending on which of those you pick, it's very important to calculate the economic return, because these are very big capital investment and big system changes. So with that, I will end it, turn it over to you, Ryan.
Yeah. There's a quick question in the chat that I think you have time to cover.
Yes.
Why do you recommend hand probe over a hydraulic probe for?
Okay. So, Clayne, good question. The reason I say that is when you're using a hydraulic probe out there, trying to get good 3 inch and 0 to 3 and 3 to 6 inch cores is tough. And also, if you're going to be sampling at a grid intensity, trying to do that with an in-cab pickup, it gets to be a lot more work than if you just run out there with a four-wheeler or side-by-side and pull it with a hand probe. Just thinking about simplicity and speed